Now AC generator. AC generator works on the principle of electromagnetic induction. When the flux associated with any coil changes, then the EMF is induced in it. Now see here, this one is the AC generator. So schematic diagram, with the help of two strong poles of bar magnets, the uniform magnetic field is established, and in this particular uniform magnetic field a rectangular coil is placed, and this coil can be rotated with respect to this axis. Okay, and this coil is connected with slip rings, and from the slip rings two terminals are taken out. Slip rings are the rings like this. Here the terminal of the coil, or we can say the end of the coil, is attached with it, and as coil is rotated, this ring also rotates. Okay, or sometimes the arrangement is like this. On this particular ring, the end of the coil is rotated, and then after two metallic brushes are attached with the slip ring, and two terminals are taken from those two metallic brushes. So across these two terminals, this one, we get the induced EMF. Now if this particular coil is rotated in this magnetic field with angular speed omega, then the flux associated with it will be continuously changing one, and it will produce the EMF. Now we know this thing, the flux associated with the coil, that is given by N B dot A. So we can write that is NBA or NAB cos theta. Theta, that is the angular displacement. If it is rotated by angular speed omega, then in time t, the angular displacement, that is omega t. So flux phi, that is NAB cos omega t. So with time t, the flux associated with this coil will be continuously changing as per cosine function. Now EMF will be induced in it. We have the equation for EMF, that is E equal to minus d phi by dt, that is equal to minus d by dt of phi, that is NAB cos omega t. NAB, that is constant, differentiation of cos omega t, that is minus omega sine omega t. So E, that is now NAB omega into sine omega t. It implies that here across two terminals of those slip rings, we get the output voltage, that is NAB omega sine omega t. It implies that our output is periodically changing as per sine function. So the maximum value of the voltage obtained, that is NAB omega. Suppose we say this is E maximum or E0, then we can say across those two terminals, we get the voltage that will change from plus E maximum to minus E maximum, or we can say plus E0 to minus E0, as sine function changes from plus 1 to minus 1. So across these two terminals, these two, we are getting output voltage, which one is continuously changing as per sine function, and therefore we can say this one is alternatively changing voltage, so AC voltage. and therefore this is called AC generator. This is also known as AC dynamo, right? In the powerhouses, when we generate the electricity at that time, we use the same principle by changing the flux associated with the coil by rotating either coil or magnets. The EMF is induced, and that is the AC generator. Very simple thing. Clear to all of you? Then after, see on the next page of textbook.
सर एक बार परिवार समझाओ सर.
This AC generator works on the principle of electromagnetic induction. Okay. Now in the figure 6.17, it is represented depending on the different positions of the coil, how the EMF is induced. So first given to you, that is the coil is perpendicular to the magnetic field like this. Okay. So in that particular case, the flux passing through the coil, that is maximum one. And EMF is not induced because at present flux is constant one. But as we rotate it, then the flux will be changing one. So EMF will be induced. So when the coil is at 90 degree, means 90 degree, that is the area vector is 90 degree. Okay, means coil is parallel to the field. So area vector is at 90 degree to the field. At that time, maximum EMF is generated. Then after, when it is rotated like this, and when area vector is at 180 degree with respect to the field, in that particular case again, the EMF will be 0, and then after EMF will be -1. Clear? So in this way, the EMF is induced as per the rotation of the coil, that is represented here in the graph. So at what time you will get maximum, minimum EMF, that is also mentioned here. So when this one is changing as per sine function, so sine function, that will be 2 times 0 and 2 times maximum in one period, right? So at t/4 time, it will be maximum. At t/2 0, at 3t/4, it will be again maximum, but it will be negative. And again at time t, it will be 0. So in this pattern, the EMF will be induced across two terminals of the coil. Clear to all of you? Any doubt in this one? Example 6.8. Refer to figure 6.12a. The arm PQ of the rectangular conductor is moved from x equal to 0 outwards. The uniform magnetic field is perpendicular to the plane and extends from x equal to 0 to x equal to b, and is 0 for x greater than b. Only the arm PQ possesses substantial resistance small r. Consider the situation when the arm PQ is pulled outwards from x equal to 0 to x equal to 2b, and is then moved back to x equal to 0 with constant speed v. Obtain expression for the flux, the induced EMF, the force necessary to pull the arm, and the power dissipated as Joule heat. Sketch the variation of these quantities with distance. Now see, this conductor PQ is moved from SR, means x equal to 0 to x equal to 2b, and then from x equal to 2b to x equal to 0, right? So in this way it is moved. Now see, when at any instant the position of the PQ is as shown in the figure, which is at a distance x from RS side, then flux associated with this loop formed, PQRS, okay, that is B into area. So area of the loop, that is length into breadth, okay. So we can write flux phi, that is BLX. And now this equation for the flux, that is valid up to B, as this X changes. Here we have to change this X, that is changing from 0 to B. So when the rod is moved from RS to B, the flux is changing as per X. But when it reaches at B, the flux associated with the loop, that is BLB. But after that, if we move this one up to 2B, then B to 2B, there is no field. See in the figure. It implies that flux associated with this loop formed, if PQ is anywhere in between B to 2B and up to 2B, the flux associated, that will remain BLB, because in this portion flux is not associated because field is not there. So for the region 0 to B, the flux can be written as BLB, that is variable one. But after B up to 2B, flux will be constant, and that will be BLB. Clear to all of you? Okay. Now EMF induced, that is d phi by minus d phi by dt. So minus BL dx by dt, that is minus BLV. But when we use this BLX, means this EMF is induced during the motion of the rod between 0 to B. But when we think about the EMF induced during its motion from B to 2B, then the flux is constant one. So differentiation of constant will come to 0. So in that particular region, B to 2B, EMF will be 0. Then force. Force is BIL, I, that is E by R. So force, that is equal to minus B square L square V by R, and V, that is the velocity of this particular conductor when it is moved. But when we think about the force, then force is required only when the EMF is induced, because when EMF is induced as per Lenz law, that EMF will produce the current in such a direction so that it opposes the cause of its production. So the EMF is induced in the region 0 to B. So force that we have to apply for this particular region. But after that, the EMF is not induced. EMF is 0. So no need of force. Force will be 0. Now Joule heating loss, that is I square R, I, that is E by R, so we can write resultantly E square by R. E, that is B VL, so B square V square L square upon R. But Joule heating, that will be obtained in the region 0 to B only, because in this region when rod is moving, the EMF is induced. After this one, EMF is not induced. So in the region B to 2B, the loss in the form of heat, that is 0. Now if you want to draw the graph, then very simple. See, for flux 0 to B, flux is increasing, then B to 2B, then 2B to B, and then B to 0 decreasing 1. Clear? So in this way we can prepare the graph of flux. Then EMF. So during the change in flux, EMF will be induced. Then after it remains 0, and then again EMF induced. But here, as per minus d phi by dt, slope of this one, that is positive. So EMF is negative. Okay. And when the slope d phi by dt, that is negative, EMF induced will be positive. So force will also follow this EMF. Clear? Because F equal to BIL and I, that is E by R. And power, so that is E square by R. In this region or in this region, when we take the square, it implies that the power loss, that is positive always. Clear to all of you? Or any doubt, any question? Next one. Two concentric circular coils, one of small radius R1 and the other of large radius R2, such that R1 is very much less than R2, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. Now see, we have two coplanar concentric rings, one that is with radius R1, another one that is with radius R2. Now we want to find the mutual inductance of this system. So as per definition, mutual inductance of the system, that is nothing but the total flux associated with either of the coil due to unit current passed through the other one. So here, let's pass the current through this larger ring, means the outer one, and suppose the current is passed through it, that is I2. Now, due to this particular current passed through
सर अनम्यूट करो.
Now, if the current I2 is passed through the outer ring, then the magnetic field is produced at its center where the smaller ring is placed. So, magnetic flux associated with that smaller one, that we can write phi1 equal to B2 into A1. B2, that is the magnetic field produced by this outer current carrying ring, and that is mu 0 I upon 2R. So that is mu 0 I2 upon 2R2. And area of the smaller ring, which one is placed at the center, that is pi R1 square. Here R1, that is very much less than R2. If we take this condition, then and then only we can treat this field at the center as constant. Now, flux phi1, that is, this equation is rearranged, mu 0 pi R1 square upon 2R2 into I2. And that is equal to, now as per definition, we can write M12 I2. So M12, that is, or we can write M12 itself is M21, or simply you can write that is equal to M. So that is mu 0 pi R1 square upon 2R2. This is the mutual inductance. Clear to all of you? Then after, example 6.10. A. Obtain the expression for the magnetic energy stored in a solenoid in terms of magnetic field B, area A, and length L of the solenoid. B. How does this magnetic energy compare with the electrostatic energy stored in a capacitor? Now see, magnetic energy stored in the solenoid, for that we already derived the equation in theory, right? And this particular equation of the magnetic energy, that is half Li square. Now in question it is asked to you, derive this equation in terms of B, A and L. L, that is the length of the solenoid. So we have to introduce B, A and L in this equation. Now L, that is the self-inductance of the solenoid or inductor. And for that also we derive the equation L equal to mu 0 N square A into L. Then we know this thing, magnetic field produced by the current carrying solenoid inside it at any point, that is mu 0 N I. So here make N as a subject. So I, that is B upon mu 0 N. Now substitute this value of inductance L in this equation, as well as I, that is B upon mu 0 N, substitute it here. So magnetic energy, that is half into mu 0 N square AL into B upon mu 0 N whole square. Now half mu 0 N square AL as it is. This one can be written as B square upon mu 0 square N square. 1 mu 0 will be cancelled here. N square will be cancelled. Resultantly, you will get the magnetic energy stored in the solenoid in terms of BAL, that is half B square upon mu 0 into AL. Now A, that is the area of the solenoid, L, that is the length of the solenoid. So area into length will give you total volume. Now if we divide this energy stored in the solenoid by the volume of the solenoid, then we will get the energy stored per unit volume. And energy stored per unit volume itself is called energy density. Is called energy density. Clear? So energy density in the solenoid, that is magnetic energy upon volume of the solenoid, that is UB upon AL. So we can write, if we take this AL on left hand side, then energy stored per unit volume, or we can say energy density of the solenoid, that is B square upon 2 mu 0. The same type of equation we derived for the energy stored in the capacitor per unit volume of it, and that is half epsilon 0 P square. So see here, there is the analogy between the constant. In magnetics, the constant is 1 upon mu 0. In electrostatics, that is epsilon 0. Here the magnetic field is there. Here the electric field is there. Clear to all of you? Then example 6.11. Kamla pedals a stationary bicycle. The pedals of the bicycle are attached to a 100-ton coil of area 0.1 meter square. The coil rotates at half a revolution per second, and it is placed in a uniform magnetic field of 0.01 Tesla, perpendicular to the axis of rotation of the coil. What is the maximum voltage generated in the coil? Very simple thing. Total number of turns in the coil, that is 100. Area, that is 0.1 meter square. The magnetic field in which it is placed, that is 0.01 Tesla. And the angular speed with which the coil is rotated, that is 0.5 revolution per second. So convert it in radian per second by multiplying with 2 pi. So your omega will turns to pi radian per second. Okay, that turns to pi radian per second. Now maximum voltage obtained here, that is NAB omega. N 100, A 0.1, B 0.01 omega, that is pi. You will get the maximum voltage obtained here. Clear to all of you? 6.1. Predict the direction of induced current in the situations described by the following figure. 6.18 A to F. Now see, in all these figures, to predict the direction of the induced current, we have to use Lenz law. We know this thing. As per Lenz law, the direction of induced current, that will be in such a direction so that it try to oppose the cause of its production. Okay. Now see, suppose we think about figure number A. Then the end of the coil Q, that is facing to the south pole of the bar magnet. Now bar magnet is moving towards the coil. It implies that now the current induced in the coil will oppose this motion, and that is possible only if the Q end behave as a south pole. Now to induce a south pole at Q end, the current constituted, that will be in the clockwise direction. That will be in the clockwise direction. Clear to all of you? Any doubt in this one? Then after, second figure. In that, see, for the PQ coil, Q end is facing to the south pole of the bar magnet, and north pole is facing to the X end of the XY coil. So when the bar magnet is moving towards the PQ coil, so here the EMF induced will produce the current in both the coils, will oppose the cause of its production. Now see here, magnet is moving towards PQ, so it will repel it. But with respect to XY, it is moving away, so it will try to attract it. It implies that Q end, that will be south pole, in that direction the current will be induced, so clockwise. But X end, that will be also south pole to attract the magnet, so at X end of the coil also the current induced will be in clockwise direction. Then after, see, tapping key just closed. So if tapping key is just closed, then the current increases from 0 to I. So against it in the coil XYZ, the current induced, that will be in the opposite direction of this current, because your current is increasing 0 to I. So induced will try to decrease its effect. So it will be induced in opposite direction. So current induced in coil XYZ, that will be in the direction XYZ. Similarly, in D figure, same type of situation, rheostat setting being changed. So current, that is always from positive to negative terminal of the battery. So here, if the current is from positive to negative, then in the opposite direction of it, the current will be induced in the opposite coil XZY direction. Clear? Similarly, in this figure E, tapping key just released. So if you release the key, then current will decrease from I to 0, but the direction of current will be the same one. Just the magnitude of the current decreases. Current will be from positive to negative. But suppose the current is from positive to negative and it is 10 milliampere. As soon as you release it, then that will decrease 10, 9, 8, 6 like that and become 0. But the direction, that will be the same one. So positive to negative direction of the current will be there in first solenoid. So in the other solenoid, in the opposite direction of that current will be induced. So that current induced will be in the direction XRY direction. Then after current decreasing at the steady rate, but the current that is in the wire, so no induced current will be there. Clear? Then after 2, use Lenz law to determine the direction of induced current in the situation described by figure 6.19. Okay. A wire of irregular shape turning into a circular shape, and B, a circular loop being deformed into a narrow straight wire. Very simple thing. Now, this irregular shaped coil is or ring is placed in the uniform magnetic field. Magnetic field is perpendicular to the plane of paper going inside. Okay. Now, here if the current is passed through this particular wire, then if we think about infinitesimal small current elements, IDL like that, then on each and every current element, the force due to this magnetic field, that should be in outward direction. That should be in outward direction. So at each and every point on the periphery of this one, if the force acting that is in outward direction, then resultantly this particular will be a perfectly circular ring. Clear? So if you want the force on the current element IDL in outward direction as shown in this figure by this arrow, then as per right-handed screw rule, IL cross B, in that direction the force will be there. So as per that, we have to pass the current in anti-clockwise direction. Clear? Okay. Now here the ring is given, perfect circular ring is given to you, and you want to deform it. So to deform this one, the force that should be towards the center of this, so its shape will be changed as shown in this figure by this dotted line. But now see here no need to use right hand screw rule and everything. Just logically you can give the answer. In this particular field, through this wire, if the current is in anti-clockwise direction, then the force that is outward. Now, if force is in clockwise direction, then force will be inward. Very simply you can say. But see here, field is changed. Here the field is going inside, perpendicular to the plane. Here the field is reversed. It is outward. So keep the current as it is in anti-clockwise direction. So if the direction of the field is changed, then direction of the force here outward, that will become here inward. So simply you can say keep the current that is anti-clockwise. Clear to all of you? Any doubt in this one? A long solenoid with 15 turns per centimeter has a small loop of area 2 centimeters square placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, what is the induced EMF in the loop while the current is changing? Now see, here the number of turns per centimeter, that is 15. So number of turns per 100 centimeter, that will be 1500, and 100 centimeter, that is 1 meter. So we can write the number of turns per unit length, that is 1500, that is per meter. Area given to you, that is 2 centimeters square, so that is 2 into 10 raised to minus 4 meters square. Current changes from I1 equal to 2 ampere to I2 equal to 4 ampere. Now delta T, the time interval during which it is changing, that is 0.1 second. Now what is the induced EMF that we want to calculate? So induced EMF, that is delta phi by delta T. So that is phi 2 minus phi 1 upon delta T. Okay. Now EMF induced, that is delta phi by delta T, that is phi 2 minus phi 1 upon delta T, that is equal to phi 2, that is AB2, phi 1, that is AB1. Area is constant 1. Magnetic field is changing. Okay. So take area A common, B2 minus B1 upon delta T, area as it is. Now the magnetic field produced by the solenoid, that is given by mu 0 n I. So when the current is I2, the field is mu 0 n I2. And when the current is I1, the field, that is mu 0 n I1. Again take mu 0 n common. So finally your equation turns to mu 0 n I2 minus I1 upon delta T. Now substitute the values, mu 0 4 pi into 10 raised to minus 7, n, that is 1500, area, that is 2 into 10 raised to minus 4, I2 minus I1, that is 4 minus 2 upon delta T 0.1, you will get the answer. Clear to all of you? Then after example 6.4. A rectangular wire loop of side 8 centimeter and 2 centimeter with a small cut is moving out of the region of uniform magnetic field of magnitude 0.3 Tesla, directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 centimeter per second in the direction normal to the longer side and shorter side of the loop? Now for how long does the induced voltage last in each case? Try to understand the situation given to you, that is like this. See, this one is the loop, length, breadth. Now magnetic field, imagine it is perpendicular to the plane of this one, means like this. Now if this particular coil is moving in this way, આ રીતે મૂવ થતી હોય માનો કે, બરોબર છે, એટલે perpendicular to breadth એની વેલોસિટી હોય આ બાજુ, બરોબર છે. તો એવા કેસમાં શું થાય કે જો આ આમ મૂવ થાય તો magnetic field lines will be cutted by breadth. So across two end of the breadth the field EMF will be generated. And if it move like this, then if it move in this direction, means velocity is perpendicular to the length, then length will cut the field lines, so EMF will induced across the length, not across this one. Clear? So both these we have to calculate, and then we have to calculate for how long it will be in the length or breadth, the EMF. Now see, suppose this one is moving like this, so length will cut the field line, but this process will continue till the distance covered by the coil is exactly equal to breadth. When the distance covered by it equal to breadth, એટલે પછી એ ફિલ્ડ ની બહાર આવી ગઈ. તો કોઇલ ફિલ્ડ ની બહાર આવી જાય તો બસ પછી EMF ના થાય. હવે જો આ રીતે મૂવ થાય આમ, આ રીતે, બરોબર છે? આમ ક્લિયર? તો લેન્થ જેટલું ડિસ્ટન્સ કવર કરવામાં જે ટાઈમ લાગે એટલા ટાઈમ સુધી EMF સસ્ટેઇન થશે. After that, EMF will be zero because after that it will be outside the field. એટલે આ ખાસ સમજવાનું છે આની અંદર. Length is 8 centimeter, 8 into 10 raised to minus 2 meter. Breadth that is 2 centimeter, 2 into 10 raised to minus 2 meter. Now the magnetic field that is 0.3 Tesla. Speed with which it is moving that is 1 centimeter per second. So that is 10 raised to minus 2 meter per second. Now for longer side, EMF induced that is BVL B 0.3 V 10 raised to minus 2 L 8 into 10 raised to minus 2. So when across the longer side the EMF is induced at that time, it is moving perpendicular to the longer side. So to come out of the field, it have to cover the distance equal to breadth. So time taken, that is breadth upon speed. Breadth that is 2 into 10 raised to minus 2 upon speed that is 10 raised to minus 2, and that is 2 seconds. Similarly, for short side, the EMF induced that is BVB that is equal to 0.3 into 10 raised to minus 2, B that is 2 into 10 raised to minus 2, and you will get this much voltage. Now, when it is moving perpendicular to breadth, then time taken by it to come out of the field, that is equal to length upon speed. Length is 8 into 10 raised to minus 2 divided by 10 raised to minus 2. Your answer will be 8 seconds. Clear to all of you? Then after 6.5, a 1 meter long metallic rod is rotated with an angular frequency of 400 radian per second about an axis normal to the rod, passing through its one end. The other end of the rod is in contact with a circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. Calculate the EMF developed between the center and the ring. So we already derived the equation for the EMF induced in this type of cases in one illustration, and that equation is half d omega L square. Now see here, the length is given to you 1 meter, omega that is 400 radian per second, and B that is given to you 0.5 Tesla. Substitute values, you will get the answer. Very simple example. Clear? Then 6.6. A circular coil of radius 8 centimeter and 20 tons is rotated about its vertical diameter with an angular speed of 50 radian per second in a uniform horizontal magnetic field of magnitude 3 into 10 raised to minus 2 Tesla. Obtain the maximum and average EMF induced in the coil if the coil forms a closed loop of resistance 10 ohm. Calculate the maximum value of current in the coil. Calculate the average power loss due to Joule heating. Where does this power come from? Radius that is 8 centimeter, so that is 8 into 10 raised to minus 2 meter. Number of tons in the coil that is 20 given to you. Omega that is 50 radian per second. and the magnetic field in which it is placed, that is 3 into 10 raised to minus 2 Tesla, R that is 10 ohm. So E that is equal to NAB omega sine omega t. We derived this equation in the theory of AC generator. So the maximum EMF generated, that is this NAB omega when sine omega t, that is 1. So E maximum, that is NAB omega, N that is 20, A that is pi, R square, R that is 8 into 10 raised to minus 2 whole square, B 3 into 10 raised to minus 2, omega that is 50. Substitute all these values, we will get the answer. Now, average EMF induced. So if you want to calculate average EMF, then you have to take average of this E equal to NAB omega sine omega t. But in this equation, NAB omega, that is constant one. Okay. This one is variable one. So we have to take average of this one. So NAB omega, average of sine omega t, but average of sine omega t over one period, that is always 0. So E average, that is 0. Maximum current induced, that is E maximum upon R. E maximum is calculated here. Just substitute its value upon R, that is 10. You will get the answer. Then power dissipated in the form of Joule heat, that is I maximum square into R. I maximum is calculated into R, that is given to U. And this power is obtained from the mechanical power, which one was used to rotate this particular coil in the given magnetic field. Clear to all of you? Any doubt in this one? Now example 6.7. A horizontal straight wire 10 meter long extending from east to west is falling with a speed of 5 meter per second at right angle to the horizontal component of Earth's magnetic field. 0.3 into 10 raised to minus 4 Weber per meter square. What is the instantaneous value of the EMF induced in the wire? What is the direction of EMF? Which end of the wire is at the higher electrical potential? Okay. Now see, length is 10 meter, speed with which it is falling, that is 5 meter per second, horizontal component, that is 0.3 into 10 raised to minus 4 Weber per meter square. So this one is the case of motional EMF. E, that is B horizontal, VL, substitute all these three values, you will get the answer. Now this one is falling like this and magnetic field is in this direction, that is horizontal component. Okay. Now if we use here right-handed screw rule for the force acting on the charges residing in this wire, that is Q into V cross B. V is downward one. Okay. And B, that is like this. So if you rotate the right-handed screw, V to B, Q into V cross B, like this. So positive charges will be accumulated towards east, negative will be accumulated towards west. Clear? So here the end of the conductor towards east will be positively charged and towards west will be negatively charged. So east end will be at a higher potential and the direction of EMF induced, that is called west to east. Okay. Positive charges will be accumulated at east end. Clear? Then 6.8. Current in a circuit falls from 5 ampere to 0 ampere in 0.1 second. If an average EMF of 200 volt induced, give an estimate of the self-inductance of the circuit. Very simple. Okay. See, current I1 5 ampere changes to I2 0 ampere in time interval delta t, that is 0.1 second. Okay. EMF induced, that is 200 volt. So E, that is equal to minus L delta I by delta T. So that is minus L delta I, that is I2 minus I1 upon delta T. Substitute the values. E is 200 minus L, I2 0, I1 5, delta T 0.1. Calculate L. Very simple. 6.9. A pair of adjacent coils has a mutual inductance of 1.5 Henry. If the current in one coil changes from 0 to 20 ampere in 0.5 second, what is the change of flux linkage with the other coil? Now see here, mutual inductance that is given to you 1.5 Henry. I1 0 ampere to I2 20 ampere. That current changes in the time interval of 0.5 second. So what is delta phi? E, that is equal to minus delta phi by delta T, and EMF induced in the case of mutual induction, that is minus M delta I by delta T. Cancel this delta T. We will get delta phi equal to M delta I. So delta phi, that is M into I2 minus I1. Substitute the values. M is 1.5, I2 that is 20, I1 is 0. You will get the answer. Then 6.10. A jet plane is traveling towards west at a speed of 1800 km per hour. What is the voltage difference developed between the ends of the wing having a span of 25 meters? If the Earth's magnetic field at the location has a magnitude of 5 into 10 raised to minus 4 Tesla and the deep angle is 30. Now see here. Suppose these are the wings of the plane, and if the plane is moving like this, here it is given to you. Plane is traveling towards west, east to west, like this it is moving. So this is east-west direction and plane is moving in this way. So magnetic field lines will be cutted by this one. But here Earth's magnetic field that is given to you as well as angle of dip is also given to you. When this one is moving like this, then horizontal field lines will not be cutted. But if we think about vertical field lines like this, then this particular motion of the plane will cut the vertical field lines. It implies that velocity of the plane is perpendicular to the vertical component of Earth's magnetic field. So with the help of this angle of dip, first of all, we have to calculate the vertical component of Earth's magnetic field. Now see, speed of the plane that is given to you 800 km per hour. That is 800 into 5 by 18, that is 500 meter per second. Length of the wings, that is 25 meter, phi, that is 30 degree. Magnetic field of Earth, that is 5 into 10 raised to minus 4 Tesla. Now vertical component of Earth's magnetic field, that is B sine phi. B, that is 5 into 10 raised to minus 4. Sine phi, that is sine 30. You will get the answer. BV, that is this much. Now EMF induced across the wings. That is, now this one is the simple case of motional EMF. So BVL, but here B, that is the vertical component, which we already calculated. So substitute this answer. here L 25 given to you and V that is 500. Clear to all of you? Any doubt in this one?